this semester in physics we need a video project. So what are we gonna do? What?
We could quit physics.
No, we can't do that
Why not?
because we signed up for it.
Why do you do that?
I don't. No. Okay. All right. So I'll jump in the first idea. How about a Rubik's tube?
Okay, I like that. But how about a Rubik's tube shaped like a house?
I don't know why it'd be shaped like a house, but maybe let's keep going. Let's keep going. What do you think?
How about we just build a giant flamethrower?
Oh, yes, I'll get the hairspray.
No. We're not building a flamethrower. I don't trust either one of you with the flamethrower.
Honestly, that's a good one.
Okay. So next, how about a railgun?
What's a railgun?
You don't know what a railgun? No. We'll keep going.
No,
We'll keep going. Next, how about?
What about the thing that?
Oh yeah,
Yeah, with the sling and the pin. And
I think it's called a trebuchet.
No, it's French. Trebuchet.
No, it's a trebuchet.
I think you were
Sure?
lied to.
No, it's a trebuchet.
Oh, okay.
Let's cut to the montage of us building it.
A trebuchet is a medieval siege weapon, which basically means it was designed to throw very heavy things a very long way. In other words, it was designed to create projectiles. In the past, when we've predicted the motion of projectiles using kinematics, we've assumed ideal conditions, for example, that air resistance is negligible. However, in the real world, as an object moves through the air, it has to push each individual air molecule out of the way, transferring energy to that medium. This frictional loss as an object moves through a medium is referred to as drag, and it occurs anytime an object is moving through a fluid, defined as a liquid or gas. The equation that governs the force of drag is 1/2 rho v squared CD A, where rho is the density of the medium. For example, the density of air is commonly 1.225 kilograms per cubic meter. V is relative velocity, CD is the drag coefficient, and A is the reference area. V is equal to the velocity of the object relative to the medium. So if an object moves through static air at a velocity of 5 meters a second, then V equals 5 meters a second. However, if the air is blowing back against the object at 3 meters a second, then V equals 8. An object's reference area is the surface area of the object that is actually affected by the drag. For example, if a sphere is moving through a fluid, only 1/2 of its surface area will come into contact with the medium. The drag coefficient is a dimensionless quantity which serves to quantify the force of drag on an object, usually dependent on its shape. For example, a cube will undergo much more drag than a streamlined body. This is a number you look up. Unless you go into a career in fluid dynamics, there's a very low chance you'll ever be tasked with determining a drag coefficient. But for now, it's only important to know that it shows how an object displaces fluid. Now, with this in mind, it's time to finally take a look at the Trebuchet and see once and for all how important air resistance really is.
What's going to happen is I'm going to pull this string, which will release a chain, which will drop the box with 135 pounds of sand in it. That will then swing the arm up with the sling, which will release its apogee, throwing a projectile that way.
1, 2, 3. Again. When?
So to find the magnitude of acceleration due to drag, we have the velocity and the radius of the grapefruit, rho, the drag coefficient, and the reference area.
If you plug in all the variables, you get 1.81 newtons for drag. And you plug that into A equals force of drag over mass. The weight of the grapefruit is 1 pound and the mass is 0.45 kilograms. Magnitude of acceleration due to drag is 4.0 meters per second squared.
And so, with an acceleration almost half that of gravity, and in a direction resistive to the motion, it's safe to say that air resistance is not negligible.
When an object is being acted upon by only gravity, the free body diagram looks like this. And as it goes faster and faster, drag will be greater and greater until eventually they equal. Force of weight equals force of drag. So, mass times gravity equals 1/2 rho velocity squared coefficient of drag area. So, terminal velocity equals the square root of 2 mass times the acceleration due to gravity over rho coefficient of drag times area. This is disgusting. Let's say that there was a plane flying around, maybe to some distant island, like perhaps Madagascar. Now, let's say said plane was flying at 20 whole million feet above the ground. And you were to jump out of the plane. And compared to if you were to jump out off of a building at, let's say, about 1,500 feet, if you were to jump off, by the time that both people were to jump out of said plane and said building and hit the ground, their terminal velocities would equal each other.
Oh my gosh, it's the Boston Tea Party.
Right now, we're filling up a bin for one of our bits on a drag. We didn't have enough food coloring, so we decided to use tea.